This is a pentagon, 5-sided polygon, and then let's say we join all the diagonals together. Join all the diagonals together. I have first question. How many diagonals? So this is for 5, but I want to ask in general if it is an n-sided polygon. Let's call it an n-gon. How many diagonals are there? So here, how many diagonals? Here, you don't count the outermost, you count the inner part. So there are 5 of them, right? So how do we calculate this number of diagonals? Okay, there are many ways. Okay, many ways. One is, okay, let's count all the edges first, and then we minus the outermost part. And this will give us the number of diagonals, right? So the total number of edges that we can see is, because for each vertex, it is going to have n edges joining to it. So you get n times n minus 1. These are the total number of edges. Oh, but then each edge you are over counting. You are double counting. So for this edge, for this one we are counting 1, 2, 3, 4. For this one we are counting 1, 2, 3, 4, right? So this edge is counted twice. Actually, each edge is counted twice. This edge is counted twice because for this one it's counted 1, 2, 3, 4, and for this one it's counted 1, 2, 3, 4, right? Each edge is counted once by one of the endpoints and counted at another time by the other endpoint. Okay? So the number of diagonals should be equal to n times n minus 1 divided. Okay, so n times n minus 1 divided by 2 because it's overcounting it. And then finally you minus n. Does that make sense? Okay, so this is the handshaking theorem. Okay, to count the number of edges in a graph, you add up all the degrees and then divide it by 2. Okay, each vertex has n minus 1 as its degree. So n of them, the total degree is n times n minus 1. And finally, you divide it by 2 because each edge is counted 2 times. So these are the total number of edges in this graph. But we want diagonals only, so we minus n at the outermost. Okay? Another way. For this one, this is also called a complete graph. This is called a complete graph because you have an edge between any pair of vertices. Okay? Right? So how many edges are there? This is easy. This is a combinatorics problem. You pick any 2 vertices, there is 1 edge. So there are n choose 2 ways to pick 2 vertices. Is that okay? So the total number of edges is equal to, it is n choose 2. These are the total number of edges. And then you want to minus n because this represents the diagonals. Is that okay? Okay, good. So this is the first question, okay? Now the second one. Number of intersections by the diagonals. How many intersections are there? So here in this graph, there's 1 intersection point here, 2 intersection points, 3 intersection points, 4 intersection points, 5 intersection points, right? But there are 5 intersection points. So is it like we have 5 diagonals and then each intersection point comes from 2 diagonals? So 5 choose 2. Well, 5 choose 2 is 10. And then it doesn't make sense. This is correct, right? So there are 5 diagonals here, but then there are just 5 things here. The reason is that some pair of diagonals, like this one and this one, does not make an intersection. Okay, it makes an intersection here at the vertex. Okay, but okay, so you may think of this as, oh, is it like the so any pair of diagonals, you choose 2, so you make an intersection, but then you minus the 5 of them, and then you get the answer. Well, let's take a look at the case when n is equal to 6, and let's see what will happen. So this one, so for this question, I need to make an extra requirement. So we assume that no 3 diagonals, they are how do you concur? They are so any 2 so no 3 diagonals cross at the same point. So I'm making this assumption. So let's take a look at the case when there are 6. So 6 is like this. So we have 1, 2, 3, 4, 5, 6. Okay. So we have a diagonal like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now this is the 9. I have not joined this one and this one. So this is like this. Okay, so I don't want to cross at the same point here, but this is still a diagonal. Okay, so it doesn't. So although I'm making this curly, yeah, but it doesn't increase or decrease the number of intersections. So let's count the number of intersections here. Yeah, although it is very strange, but so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15. So there are 15 intersections. So n is equal to 6. There are 15 intersections. So how do we get this? So here, if you look at it, this is a diagonal, and this is another diagonal. These 2 diagonals looks like they are parallel to each other. So they don't make any intersection at all. So it seems like it is not the number of diagonals choose 2 and then minus something. It is not that. So is there a way to? Okay, so let's see. How do we specify an intersection? So there is an intersection. There's an intersection. How do we specify it? How do you describe? There's an so. For any intersection that we look at, what will happen? It must come from 2 diagonals, right? 1 diagonal, 2 diagonals, right? Right? So these 2 diagonals form an intersection, right? And these 2 diagonals just form this one single intersection, right? Right? And then how do you describe these 2 diagonals? These 2 diagonals comes from this as a vertex, this as a vertex, this as a vertex, and this as a vertex, right? So when we look at these 4 vertices, we get an intersection. Is that okay? If we look at another 4 vertices, what will happen? If we look at another 4 vertices, so whenever we look at 4 vertices, 1, 2, 3, 4, whenever we look at these 4 vertices, we are going to consider what? We are going to consider this as a diagonal and this as a diagonal. Am I correct? And then we get one intersection. Okay? So the answer of this one, let's see if you agree, it is going to be n choose 4. Is that okay? Whenever you pick 4 vertices, it would define exactly one intersection. whenever you pick 4 vertices, whenever you pick, we look at the opposite pair to join as diagonals, and then it defines an intersection. So if any 4 defines an intersection, and any intersection will define 4 vertices. So there is a one-to-one mapping, one-to-one correspondence between the diagonals, the intersections and a 4-sided polygon. Is that okay? So this is n-choose 4. Difficult, not easy. Not easy. Okay, the third question. Okay, this is related. The third question is now. But amazing, right? So even this kind of problem, it is a combinatorial problem. We are doing n-choose 4, n-choose 2. Okay, the third one is the number of segments coming from the diagonals. So here, what I mean is that, so we have intersections by the diagonals. So this intersection is like cutting the original diagonal into different segments. So there's one segment here, there's a second segment here, there's a third segment here, there's a fourth segment here. Is that okay? So these are the segments that I'm talking about. So you have many segments here for this example. For the pentagon case, then the segment is easily counted. There are going to be how many of them? There are going to be 15 of them. Because for each diagonal, it is uniformly cut as 3 segments. And there are 5 diagonals, so 5 times 3 is equal to 15. But look at this. This is not the same. This is not the same. There are altogether 9 diagonals here. 9 of them. But some, you get more. So this one you get 1, 2, 3, 4, right? Let's look at this one. This is 1, 2, 3, 4, 5. Is that okay? Actually, for this one, 6 of them you get 4, and then 3 of them you get 5. So this is going to be 39. So for the case of n equals to 6, there are going to be 39 segments. So this one has 5, this one has 5, this one has 5. But all the other cases, the other cases, each one of them has 4 of them. Yeah. Okay. So this is 39. And now, how do we get 39? So the hint is this value is based on the value of 1 and the value of 2. 1 counts the number of diagonals, 2 counts the number of intersections. So it is based on the values of 1 and 2. So it turns out that the answer should be equal to, so this is the answer. Let's check, okay. The answer is equal to the value of 1 plus 2 times the value of 2. Let's see if I'm correct. Okay. Okay, for n is equal to 6. For n is equal to 6, how many diagonals? There are 9 diagonals. And how many intersections are there? 6 choose 4 intersections. 6 choose 4 intersections is 15. So 9 plus 2 times 15 is equal to 39. Okay, this is correct. Now, explain. Yeah, we need an explanation. So why each intersection represents 2 segments? This is like that, right? Originally, let's say we don't make any intersections. All the diagonals, they are happy together. They don't cross. Okay, they don't touch. They are just 9 separate lines. So 9. And suddenly, 2 of them touches. There will be 1 new intersection point. Okay, then what will happen? Originally, there are just 2 happy lines, and then they touch, and it becomes 4 unhappy lines. Each one of them becomes shorter, right? So this intersection point has the effect from making 2 into 4. Okay. And then if we have another intersection somewhere else, then that will be corresponding to 2 happy lines becoming 4 unhappy lines. So that means what? Each intersection is going to add 2 segments. From 2 to 4, and then here. From 2 to 4, there. From 2 to 4, there. Whenever there is one intersection appearing, you add 2. So that's why if there is no intersection, you just have 1, the result of 1, the number of diagonals. But if you have intersections, each intersection corresponds to 2 new segments. So this is it. So amazingly, the number of segments, you can still represent it using the combinatorial terms. We have just 5 minutes, right? But I'm getting some kind of forgetful. Did I ask you any IQ question last time or whatsoever? No? Okay, good. Then this is an IQ question for you. So to end today's class. Okay, so there are a couple of examples. Let's do it on Thursday. So today's thing is, I want to ask you to find the proof why this is true. So there is a kind of a game called Rubik's Cube. This is a 3 by 3 by 3 cube. You can twist it, right? Okay, let's say this is like a really cube. So in Rubik's Cube, the center is some machines, right? It allows you to rotate. But let's say you have a large cube, and then you want to cut it into this 3 by 3 by 3 into 27 pieces. Okay, now you can. So one way to cut it is like this. You borrow a knife, you cut it one, and then you cut it like this, and then you cut this time, you cut this time, and then you cut this time, you cut this time, right? You can use 6 cuts to make it into 27 pieces. But now, let's say I allow you to do something fancy, okay? So you can do the first cut it somewhere, cut. After cutting, you can put the blocks one over the other, maybe this one over the other, or you can shift it or whatever. Once you place it, you can use your knife again and to cut it again, okay? After you cut it, now if you cut it for the first time, you get 2 pieces, right? And then you cut it the second time, maybe you get 4 pieces. You can do any arrangement you like. And then you cut it again. And then you do many arrangements again. Once you have arranged it, you cut it again, okay? Now, this is becoming more flexible than what you can do at the beginning. At the beginning, you cannot move anything. But then 6 cuts is okay. Now, I allow you to move. Then is it possible that we can do it in 5 cuts? Yes, give me a way, of course. No, tell me why this is not possible. Now, 4 cuts is not possible. The reason is that for each time you cut, you only double, at most double the number of pieces. So if you have 4 cuts, then you can make only 16 pieces, but there are 27 pieces. So 4 cuts is never possible. Now 5 cuts may be possible because 2 to the power 5 is 32. You may be very clever so that you can make it into using only 5 cuts. Now the question here is that whether 5 cuts is possible or not. Find a proof that if it is possible, give me a way. If it is not possible, give me a proof. Okay, as short as possible. Okay. Okay. So let's don't make this super hard. Let me ask you. What do you think? If you think it is possible, could you please raise your hand? Okay. Okay. Good. If you think it is not possible, could you please raise your hand? Nobody? 1, 2. Okay. Now, okay. I'll tell you. The answer is not possible. Now, so I tell you the answer. But then, this is not the end of the story. For you, try to find a proof why it is not possible. Try to find something that 5 Never. But you need at least 6. Okay. Okay. So let's talk about this problem on Thursday. Okay, and then let's end the class early today.